Hello, everyone. We're happy to have Camille Horbez give his third talk on measure equivalence rigidity.
Thank you. So yeah, today I'm going to talk about super rigidity phenomena for measure equivalence. So I should say that if you were scared last time by the definitions of Madhava and normalized sub-equivalence relations, I won't use them anymore. In some sense, it's going to be more in the spirit of the first lecture using couplings. Okay, so let's start with the statements. So maybe the first rigidity theorem in measure equivalence is a theorem that was proved by Furman, building maybe on earlier work of Zimmer, and he proved the following, that if you take a lattice in a higher rank simple Lie group, and if you have another countable group lambda, lambda is measure equivalent to gamma, then automatically you get a very strong conclusion, which is that lambda essentially also has to be a lattice in the same Lie group. So lambda is virtually isomorphic to a lattice in G. Right, so I remind you that virtually isomorphic here means that, so this is true up to maybe passing to a finite index subgroup and taking a quotient by a finite normal sum. Okay, so this is a very strong rigidity result, which sharply contrasts with, for example, what we saw with the Madhava groups, which are all measure equivalent to one another. Here, if you have a group that's measure equivalent to gamma, then there's not much possibility. You have to be a lattice in the same group. So in this lecture, I will talk about groups that are, in a sense, even more rigid than this, in the sense that they won't even be an invariant Lie group. So I will say that countable group gamma is measure equivalence rigid if you get the strongest possible rigidity statement that for every countable group lambda, if lambda is measure equivalent to gamma, then, well, they have to be virtually isomorphic. And so in a sense, there is no natural invariant Lie group for gamma, apart from gamma itself. Okay, and the main theorem is that we know that some groups satisfy this strongest possible form of rigidity. So the first class of example is mapping class groups. This is a theorem of Kida that if you take a surface, say an oriented connected surface of genus G, to which you can possibly remove a finite number of points, and you look at its mapping class group, which I remind you is defined as the group of all isotopy classes of orientation preserving homeomorphisms of the surface. This is super rigid in measure equivalence, unless, of course, in some low complexity situations where the mapping class group is too small. So you need to exclude spheres with at most 4 punctures, because then the mapping class group is either finite or virtually free, and those are not super rigid. And you also need to exclude the torus with at most 1 puncture for the same reason. You get a virtually free mapping class group. But apart from this, they are all super rigid. Okay, with Girardet, we proved that the outer automorphism group of any non-abelian free group of rank at least 3 is also super rigid in measure equivalence. So again, I'm excluding n equal to 2 because out F2 is known to be isomorphic to GL2Z, which is virtually free and you don't have rigidity. There is another class of groups which somehow interpolate between those two. This is a theorem with Sebastian Hensel, that the mapping class group of any handle body, 3-dimensional handle body of genus at least 3, is also super rigid. So what do I mean by handle body of genus at least 3? So this is the, so it looks like I'm drawing a surface, but in fact I'm drawing a 3-dimensional manifold whose boundary is this surface, right? So here there is a disk, and the surface is the boundary of the manifold. And the mapping class group is defined the same way. So as a matter of fact, the mapping class group of the handle body embeds in the mapping class group of its boundary, the Youngbian surface. And if you look at the action of the mapping class group on pi1, which is a free group, so you get a homomorphism from the mapping class group to out Fn. So in a sense, this class of groups is kind of intermediate between mapping class groups of surfaces and out Fn, and there is a lot of work in trying to understand which properties from those groups can the handle body group have. Okay, let me add 2 more. With Jingyin Huang, we proved that many Artin groups are super rigid in measure equivalence, but I should say that right angle Artin groups are not. Reason being that right angle Artin group, I'll say maybe more about this tomorrow, but briefly the reason is that a right angle Artin group is always measure equivalent, in fact even orbit equivalent to any graph product of countable amenable groups over the same graph. But okay, let me give an example of an Artin group that's super rigid in measure equivalent. So let's say you generated by at least 4 elements, and then the relations is that, so you imagine that you write those elements along an n-gon, and for every edge of this n-gon, for every I considered modulo n, I add a braid relation. So I require that if you do AI plus 1 AI, then this is the same as AI plus 1 AI. AI plus 1. Yes?
So this thinking that I've made about drags, So you have the same when you replace the series by the mean.
Yes.
That's the
Yes, exactly. Yes. Graph product over the same graph. And,
and the rigidity of that sort of
there are things, yes. So maybe I'll say more about this tomorrow. But for example, you can prove that the rag over a pentagon and the rag over a hexagon are not measure equivalent. Like so you can you can in fact for rags with finite outer automorphism group, among the class of rags with finite outer automorphism group, being measure equivalent is the same as being isomorphic. At this point, there is no statement of the form. Well, it's not true. Yeah, like you could say maybe a group that's measure equivalent to a rag is a graph product of amenable groups. As such, it's not true. There are other examples coming from lattices in the automorphism group of the Salvetti complex of the rag, which are not graph products. But you can get some rigidity statements if you impose the right conditions, and you can prove that.
There's still you're locally compact.
Yes, but the graph product of amenable groups does not act on the Salvetti complex. This is not the lattice in the automorphism. So the situation is more complicated. One can still say something, and maybe say more. Okay, the last family of groups I want to mention is Higman groups. So these are groups that were introduced by Higman in the 50s as the first examples of finitely generated, finitely presented infinite groups with no non-trivial finite quotients. And they are still very mysterious in many ways. Sometimes they are thought as a possible candidate of a non-Sophic group, but nobody knows. So they are defined in the same way as those ordering groups. So you start with an n-gon, but now on each edge, you put a Bohm-Slack solitary relation. If you conjugate, say, AI plus 1 by AI, you get AI plus 1 squared. Okay, so all these groups are super rigid in measure equivalence in the strongest possible sense, that if you have a group that's measure equivalent to one of these, then it has to be isomorphic to finite index of groups and taking quotient by a finite normal set. I don't know any examples that. Yes, right.
Based on the Higman group example.
Right. So these have no finite index subgroup, but they have some. Yeah. I don't know. I should say. So this is not a complete list of all groups that are known to be super rigid. There are so. Kida has things about, like, if you take the Torelli subgroup, the mapping class group, it will also be super rigid. He also has examples of groups that are built as amalgamated free products of, I think, of some linear groups, and where you have to choose the amalgam carefully. So, but there are not that many other known examples of groups that are super rigid in this sense. I should say also that as far as quasi-isometry is concerned, so the QI rigidity, so the analogous statement that a group that is QI to gamma has to be virtually isomorphic to gamma is known for mapping class groups and for Artin groups, but it's still an open problem for out-FN, Handel-Bott groups and Higman groups. Okay, so my plan for well, today and tomorrow is, so I would like to explain you some of the ingredients in the proof of this theorem, but I will start by presenting you some more geometric consequences of this. Maybe one thing I should first say is that, so when you try to prove QI superrigidity of a group, often the first step, not always, but often, one thing you want to do is first compute the group of quasi-isometries of the group gamma itself, and show that maybe this group is not much bigger than gamma, meaning that every self quasi-isometry of gamma is at bounded distance from the left translation by an element of gamma. If you know this, then what happens is if you have a group lambda that is QI to gamma, then you manage to produce a representation of lambda in the group of quasi-isometries of gamma, and then there is some general arguments to say that this is an isomorphism, and then gamma has to be virtually isomorphic to lambda has to be virtually isomorphic to gamma. So there is no group of self-measure equivalences of gamma, but still there is a similar strategy in the ME setting. And what I mean by this is that in order to prove measure equivalence rigidity, a priori you need to prove something about couplings of gamma and lambda, ME couplings of gamma and lambda, but in fact you only need to prove a statement about self-measure equivalence couplings of gamma. So I will say that the countable group gamma is taught in measure equivalence if the following holds. So the kind of things you want to prove is that if you take any self coupling of gamma, so you have an action of gamma cross gamma on some standard measure space omega, such that each of the two actions is free with a finite measure fundamental domain. Well, you need to prove that every self-coupling factors through the trivial, the tautological one. What is the tautological coupling? Is the one where you just act on gamma itself by left-right multiplication. So essentially, you need to prove that there exists an equivariant map, measurable equivariant map from omega equipped with this action to gamma equipped with the action of gamma times itself by left-right multiplication. And if you prove such a statement, then there is some abstract argument to show that measure equivalent superrigidity. So I should say that this is not perfectly correct. You might have to allow to replace here gamma by a finite index extension, which, for example, for the mapping class group, in fact, the gamma hat will be, you will need to allow for orientation reversing homeomorphism, which is an index 2 extensions. Here, you would need to account for the order 5 symmetries. You need to allow Z mod phi Z, Z mod n Z factor. Okay, so if there exists some finite index of a group such that the following holds, maybe not even for self-couplings of gamma, but I might allow for self-couplings of finite index subgroups of gamma. But essentially, and there is one more condition that I need to add. This is actually important in this theory, is that for all of these arguments to work, you want the group gamma hat to have infinite conjugacy classes, meaning that in gamma hat, the conjugacy class of every non-trivial element is infinite. Okay, this might look like a technical condition for now, but it's actually important for several arguments. The key point is that every self-coupling of gamma factors through the tautological one. And then, so as I mentioned, so it was proved in the successive works of Furman, Ono, and Shalom, and Ikeda, that if the group is ME out in this sense, then it's super rigid in the previous sense. And I'm not going to prove this because the argument is quite abstract. But let me just say that the starting point for this theorem is that, so if you have some coupling between gamma and lambda, then there is a way of building the self-coupling of gamma by doing the same thing that I presented in the first lecture. That so you can also view, maybe people usually write sigma Chech for the coupling of lambda cross gamma, the same one, and then you can do a composition. So you can have gamma times gamma act on sigma cross sigma Chech mod out by the diagonal lambda action. This is a self-coupling of gamma, to which you can apply the tautness to get a map to gamma hat. And then if you analyze the construction from this, you manage to get a representation of lambda in gamma hat. And this is the starting point towards proving the ME rigidity from the tautness. Okay, and I'm claiming that all groups here are, in fact, taut. From this, we deduce the rigidity. Okay, so maybe before going into the proof of tautness of maybe the mapping class group, let me start by presenting some consequences. So the first thing I want to observe is that if you have a group which is taut, then you have some automatically some algebraic form of rigidity, which is that its outer automorphism group will be finite. In fact, you know exactly what the automorphism group of gamma will be exactly so you have an action of the normalizer of gamma in gamma hat by conjugation on gamma. And this is exactly the automorphism group of gamma. So let me prove this. So first of all, notice that the injectivity of this map follows from my ICT condition, right? Because if you have an element that induces the trivial automorphisms, it means that your element of gamma hat commutes with every element of gamma, and so it will have a finite conjugacy class. Okay, so how do we prove surjectivity? So let's theta the automorphism of gamma. So theta gives me a self-measure equivalence coupling of gamma, where you act by left-right multiplication, except that I will twist, say, the right multiplication by the automorphism. So I'm acting via gamma 1, gamma 2 is acting on gamma, where the left coordinates act by left multiplications, and the right coordinates act by right multiplications, but twisted by theta. Now, so I have a self-coupling, so I can apply the this assumption in M-tautness to derive the existence of a map from my coupling gamma to gamma hat, which is equivariant. So what does the equivariance mean? So on gamma, I am acting this way. But here on gamma hat, I'm acting with the action that's not twisted by the automorphism. Okay, and now if you apply this to, let's say gamma is equal to 1, and gamma 1 is theta of gamma 2. So here I have theta of gamma 2 times 1 times theta of gamma 2 inverse, I get pi of 1 is equal to theta of gamma 2, pi of 1, gamma 2 inverse, or in other words, theta of gamma 2 is equal to pi of 1 inverse gamma 2 pi of 1, which shows that theta is the conjugation by the inverse of pi of 1. So theta indeed is a conjugation in this baryon group gamma hat. Okay. So in fact, if instead of looking at self-couplings of gamma, you work with self-couplings of finite index subgroups, what this shows is that M-tautness is stronger than rigidity of commensurators, right? So more generally, instead of considering the group of automorphisms, you can define the abstract commensurator of gamma to be the group of all isomorphisms between finite index, so gamma 1 and gamma 2 are finite index subgroups of gamma. And this is a group by defining the product of two such isomorphisms to be, you just take the composition in restriction to a finite index subgroup where it's well defined. And the thing is that if gamma, the same argument essentially shows that gamma is out in measure equivalence, then the natural map from gamma hat to the abstract commensurator of gamma, right? So every element of gamma hat by conjugation gives you an isomorphism between two finite index subgroups, is an isomorphism. Right, so for example, Kida's theorem on measure equivalence rigidity of the mapping class group is a highly non-trivial extension of Ivanov's theorem about the fact that the extended mapping class group is the abstract commensurator of the mapping class group. Okay, so what is this all about? Well, essentially, when you look at the abstract commensurator, you are only considering discrete self-couplings of gamma. And I'm saying in measure equivalence, you are considering all measurable self-couplings, so you have much more information in tautness than the abstract commensurator. Okay, let me give you a second application of tautness to automorphisms of Cayley graphs. This is a more geometric application, and I would say that so for all the groups I listed, the rigidity of the abstract commensurator was somehow known before the rigidity in measure equivalence. Oh, yes. So it's discrete, right. So I guess two groups are virtually isomorphic if and only if they act on a discrete set with countable discrete set with left, right. So is that your question, or is it?
But there's also like a measurable version of commensurator. There's a big group that captures all self-coupling.
Oh, no, I don't think that there's no group of measure equivalences of gamma. But yeah, I guess I don't know if you can make a category of couplings, or I don't think it's a group structure. Right, so you would say for discrete couplings, you have commensurator. For topological couplings, you have the group of quasi-isometries, but I don't think there is a group of measure equivalences. Okay, so the second application is to automorphisms of Cayley graphs. So maybe let me just to make sure that we have the same conventions, recall that if gamma is a finitely generated group and S is a finite generating set, then the Cayley graph of gamma with respect to S is the graph whose vertices are the elements of gamma, and where you put an edge between gamma 1 and gamma 2, with gamma 1 and gamma 2 distinct, if you can find an element which is in the generating set or an inverse of a generator, such that gamma 2 is equal to gamma 1s. So what I want to insist on is that by convention, even if the identities in the generating set, I don't allow for loop edges, and even if you repeat twice the same generator in S, I don't allow for multiple edges. So two vertices cannot be joined by several edges. Okay, and what I claim is that if gamma is taut in measure equivalence and torsion free, finite finitely generated group, which is tau and torsion free, this is actually important. Then for any finite generating set of gamma, so you can consider the group of all simplicial automorphisms, all graph automorphisms of the Cayley graph of gamma with respect to S. Of course, gamma sits in there because it's just acting by left translation on itself. And I claim that this inclusion always has finite index. So all Cayley graphs of tau and torsion-free groups with respect to any finite generating set have a discrete automorphism. So this is a very strong property. If you think about just the free group, there's a Cayley graph, which is a tree. The automorphism group of the tree is much, much bigger than the group itself. I'm claiming that this rigidity in measure equivalence implies something very strong about all Cayley graphs of gamma. Okay, so let me give you the proof, and then I'll make a few comments on this statement. So the fact that gamma acts on its Cayley graph properly co-compactly gives you that gamma is a lattice in the group that I will denote G of automorphisms of the Cayley graph, equipped with the topology of pointwise convergence. Okay, so since you have a lattice, it's a uniform lattice, co-compact lattice even. I won't need this. So since you have a lattice embedding, this gives you a self-coupling, gamma times itself acting on G by left-right multiplication. Now, I'm going to use my tautness assumption to get a map from the automorphism group to gamma hat, which is gamma times gamma equivariant. And my goal will be to prove that this is an embedding. So in fact, the group of automorphisms is subgroup of this gamma. So the first thing I claim is that almost everywhere, with respect to the Haar measure on G, phi of G1, G2 is phi of G1, phi of G2. Right? A priori, this map is just some measurable map between measured space. But I'm claiming I need to improve it to a group homomorphism. Okay, so to prove this, let's consider the map from G cross G to gamma hat, which sends G1, G2 to, let's write phi of G1 inverse inverse, phi of G1 inverse G2, phi of G2 inverse. Okay, I want to, so I need to prove that this is always identical. But let me define this map and observe. Okay, this is a very easy computation, and I will not write it on the board, but you can observe that if you multiply gamma 1 on the right by an element in gamma, multiply G1 on the right by an element in gamma, so this, and use the equivariance of phi you will have a gamma inverse here that cancels, so you will not change f of G1, G2. And likewise, if you multiply G2 on the right by an element gamma prime, using again the equivariance, everything will cancel, and this is the same as f of G1, G2. And the same kind of computations also shows that if you multiply both gamma 1 and gamma 2 on the left by the same element, then you get a conjugation then you just get f of G1, G2 conjugated by gamma. Okay, so what does this mean? So the fact that f is invariant under the right action means that f descends to a map f bar from G mod gamma equipped with the right action times G mod gamma equipped again with the right action to gamma hat. Right? And here I have a Haar measure which I can push forward. I push forward the product of the Haar measures through this map F bar. And what I get is a probability measure, or I mean, finite measure, but I can always renormalize it to be a probability measure on gamma hat, which is invariant under conjugation. But a probability measure on a countable group that is invariant under conjugation must give zero measure to every infinite conjugacy class. And here, using that gamma is ICC, I deduce that mu is the Dirac mass of the identity. And this is exactly saying what I want, that the map F is almost everywhere equal to the identity. And this shows the first claim. Now, in fact, so I have proved that you have this homomorphism relation almost everywhere. There is a little automatic continuity argument, which I guess that dates back to the work of Zimmer, maybe McKay, that shows that in fact phi coincides almost everywhere with a continuous homomorphism from G to gamma hat. Okay, and once I have a continuous homomorphism, which I will still denote by phi, well, I can consider the kernel of this homomorphism. And because of the equivariance of phi, the kernel of this homomorphism is contained within a fundamental domain for the action of either the left or right factor on G. And therefore, this kernel has finite measure. And since it's a closed subgroup with finite measure, K is a compact subgroup in the automorphism group of the Cayley graph. So now you have a compact normal subgroup in the automorphism group of the Cayley graph, and I claim that in fact K is trivial, which will essentially complete the proof of the proposition. And why is this? Well, using the normality of K in the automorphism group, can see that. So if I take an element gamma, gamma prime, so this is an element of gamma, so I view it as a point in the Cayley graph. K is a group of automorphisms of the Cayley graph, so I can look at the image of gamma, gamma prime under K. And the normality of K will give me this relation, from which it's actually easy to deduce that K of 1 is the subgroup of gamma. If you take the identity element in the Cayley graph and you apply K, you will get a subgroup of gamma. Not only will you get a subgroup of gamma, but because K is compact, K of 1 is a bounded set, so it's a bounded subgroup of gamma, and therefore it's a finite subgroup of gamma. And here I'm using my crucial assumption that gamma is torsion free to deduce that K of 1 consists just of the neutral element. And with this relation, for every gamma, K of gamma only consists of gamma, which is exactly saying that K is the identity, right? And so we have proved that we have built an injection from the automorphism group of the Cayley graph to gamma hat. If you look at the definition, it's not hard to see that in restriction to gamma, you really get action of, like, if you view gamma as a subgroup of the automorphism group of the Cayley graph, you really just get the natural inclusion of gamma in gamma hats through this map. So you really, this automorphism group is comprised between gamma and gamma. Okay, do you have any questions as proof? Okay, I think it's a quite remarkable application of measure equivalence rigidity. Let me make a few comments on this. So notice that all the groups that were in my theorem, so mapping class group, out FN, Handel body groups, Harding groups, and Higman groups, they are all at least virtually torsion. So you get results for finite index subgroups of these. Okay, so I should say, so this kind of theorem was also known for torsion-free finitely generated nilpotent groups by completely different methods. This is due to Pofimov. All Cayley graphs have a discrete automorphism group. It's true for torsion-free lattices in higher rank Lie groups. This is essentially Furman's theorem, giving their measure equivalence rigidity. There is also a theorem that I like by Niemann and de la Salle. Saying that every finitely generated group has some Cayley graph, which is discrete in this sense, for which the automorphism group contains gamma as a finite index. So this is a non-trivial statement about all finitely generated groups. Every finitely generated group has a Cayley graph whose the proof is actually quite involved. It involves random walks and groups, arguments, and so this is really interesting. On the other hand, there is no good conjecture of what is the class of all groups for which all Cayley graphs are discrete. But measure equivalence rigidity gives you one way of getting them. I should say something about my torsion-free assumption. In fact, this fails if the group is not torsion-free. This is an observation by de la Salle and Teixeira that every group that has a torsion element has a Cayley graph which is not discrete. So for which the automorphism group, the Cayley graph, is uncountable. Okay, I'm not gonna prove this, but let me give you one example, which is to illustrate it. And really, if you understand this example, then it's basically the same proof for all of them. So let's take this group, Z times Z mod 2Z. Yes, yes, it's like right here. So okay, let me do it here, and then yes, I will say what this is. So okay, so the first generating set you could think about for Z times Z mod 2Z is just you take generator for Z and you take a generator for Z mod 2Z, and then you get this infinite ladder. Well, this has a countable automorphism. But the trick is to add the generator 1, 1. Maybe, yes. Okay, 1. Minus 1 is the same as 1, 1. So, and then you get this. That's your Cayley graph. And now you see that here, if you look at those two vertices, you can decide to flip them. This is an automorphism of the Cayley graph. And you can do this independently for all pairs. And that way you get an uncountable automorphism. And it's really the same proof for every group that has a torsion element. The thing is, you start with a finite generating set S. I think what they do is if you take F, a finite subgroup, and you look at the new generating set, which is look at double cosets FSF. And this is a way of above every vertex seeing the left coset of F, and you have copies of F inside the Cayley graph that on which you can do permutations independently. And okay, I will not write it, but it's really the same phenomenon that arises in all finitely generated group. Yes? Exactly what I had. So the automorphism group is countable. This actually implies that gamma is finite index in the automorphism. It's a finite index subgroup, right? I mean, the thing is, right, okay, I wrote it this way. It's equivalent to say that gamma is a finite index subgroup in the automorphism group of the Cayley graph, or to say that the automorphism group of the Cayley graph with the pointwise convergence topology is discrete. Because using an element of gamma, you can always translate back to the identity. So the question is about the stabilizer of the identity. This is a compact group, and so it's either finite or uncountable. If it's finite, then you get discrete topology, and you get the group has finite indexing. Okay, and the last comment that I wanted to make is that so if you look at this proof, something that has been proved along the way is the fact that a group that's ME tout does not have any interesting lattice embedding. In the sense that, so what this argument tells you is that, so if gamma is tout, and if G is a locally compact second countable group such that gamma sits as a lattice in G. So if you have a lattice embedding, let's call it iota from gamma to G, then automatically there exists a continuous retraction from G to gamma hat. And this is in a sense saying that gamma cannot be a lattice in G in any interesting way, right? So if you take a mapping class group, like there is a way of embedding it as a lattice, which is you do mapping class group direct product with a compact group. But there's nothing more interesting you can do somehow. If you do this, the group G, we have infinitely many connected components, one per element of the mapping class group and so on. Okay, do you have any questions so far? So what I will do now, I still have 20 minutes, is so I will start to set up the proof of the measure equivalence rigidity of mapping class groups. This is due to theta. And tomorrow I'll first finish this proof and then I'll compare with other groups. Like I want to compare with Higman groups and also tell you a little bit more about right angle origin groups and how you can still find some kind of rigidity among them, even though they're not super rigid in this sense. Okay, so gamma is a mapping class group of surface with 3G plus n minus 4 positive, and gamma hat is the so-called extended mapping class group, which means that I'm allowing for orientation reversing homeomorphisms in the definition. Okay, so I need to, and the goal is to prove that gamma is ME dot. Okay, so we have a coupling, gamma cross gamma on omega. And maybe for just for simplicity of notation, let me assume that it's a self OE coupling, meaning that I will assume that both actions have a common fundamental domain. X. So X is common fundamental domain for the two actions. And again, so this means that the two actions have the same orbits, and that if X and Y are in the same orbit for the first action, meaning that there exists an element gamma 1 in the first copy that sends X to Y, then there is an element gamma 2 in the second copy that also sends X to Y. And so I have two maps. So if I denote by R the common orbit equivalence relation, then I have two maps, rho 1 and rho 2, from R to gamma, which are giving the two elements that send X to Y. Okay, and I need to build, in some canonical way, I need to build a map from omega to gamma hat. In fact, I will explain you how to build a map from the fundamental domain X to gamma hat. And then you just have to extend it. We just have to extend it by equivariance on the whole omega. Okay, so at this point of the argument, I need to tell you about the curve graph of the mapping class group. So the curve graph, well, we've already heard about it. Let me define it. So this is the graph whose vertices are the isotropy classes of essential simple closed curves on the surface, and where you put an edge between two curves C and C prime, if in their isotropy classes they have disjoint representatives. Right, so let me draw a picture. Yes, I have my surface. So the vertices are, so each time I have a curve, which is essential, meaning non-trivial in pi 1, I have a vertex. So this curve is not allowed as a vertex of the curve graph. Also, if you have punctures, I'm not allowing for a curve that would just circle a puncture. Just bound once punctured disk. But this one is essential. I don't know, this one is also essential. And since they have disjoint representative, there is an edge between them in the curve graph. And maybe this third curve is also essential. And because it's disjoint from the red, there is an edge here. But since it crosses the yellow one, and not only does it cross, but you cannot remove the crossing by an isotropy. There is no edge between the yellow and the orange. Okay, and if you do this, you get an infinite graph on which the mapping class group acts by simplicial automorphisms, right? Sending homeomorphism sends a curve to another curve, preserving disjointness. And an important theorem by Ivanov that we will use is that, so you have a natural map. So not only the mapping class group acts, but also the extended mapping class group acts on the curve graph. So you have a map from the mapping class group, extended mapping class group to the automorphism of the curve graph, and this is an isomorphism. Right, so every automorphism of this graph actually comes from the action of a mapping class. And so I will rephrase this goal by saying that I need to build a map from X to the automorphism group of the curve graph. Okay, so how will I do it? So let's pick a vertex, the curve graph, so some curve on the surface, and I will consider SC1, which is a sub-equivalence relation of R where you just restrict the first action on X to the stabilizer of C. And you only retain the elements that can be joined by an element, by letting an element of the stabilizer of C act. So this is a certain sub-equivalence relation of R. And it would be great if for the second cocycle rho 2, this was also the stabilizer of another curve. Because if it's the stabilizer of another curve, then you get a map at the level of the curve graph sending C to C prime. This is not exactly true, but what Kida proves is that this is true if you are ready to perform a countable partition of the base space X. So what I mean by this is that there exists a countable Borel partition of X. So you cut X into countable many pieces. And what is true is that if you restrict to one piece and you only look at the restriction of your sub-equivalence relation to this piece, right? So I look at S1C, but restriction to xi times xi, right? So I only look, I take 2 points in xi that are in my sub-relation. And then it's true that this is also stabilizer of a curve that, but the curve depends on which piece of the partition you're in. For every I, there exists some curve Ci such that if you take the sub-equivalence relation generated by the stabilizer of C and you restrict it to this piece, it's also, for the second action, the sub-relation associated to the stabilizer of a curve restricted to the piece. So this is the key proposition in Kida's argument. And once you have this, then you see how to build a map from X to the automorphism group of the curve graph, which is, so if you take point X and you need to say where to send the curve C, well, if X belongs to the element Xi of the partition, so this partition depends on C, but for this element C, if X belongs to the piece Xi of the partition, I will send C to Ci. And so this gives you a way of associating to every point in X a map at the level of the vertex set of the curve graph. And I claim that, I claim that this is almost everywhere an automorphism, right? It's injective, surjective, and also if you started with two curves that are disjoint, then the curves that you get will also be disjoint. And this is the way that you build canonically this map from X to the automorphism group, and then you can lift it to omega using the equivariance to prove the trivialization of the self-coupling of nebulas. X is so it's the common fundamental domain for the action. So I first take the quotient. In general, if you have an ME coupling, you would have two fundamental domains, and then you restrict to the intersection, and it's on the intersection that you define the map. So I'm just defining the map on a fundamental domain, and then I claim you can extend it by equivariance to the whole omega to get your trivialization of the coupling. Okay, and the last remaining thing is to prove this. And so how do you prove such a fact? Well, the thing is you need to have a way of recognizing sub-equivalence relations that come from curve stabilizers. if I only give you the sub-equivalence relation without telling you that it came from a curve stabilizer, you have a way just by looking at the equivalence relation to say, oh, this had to be a curve stabilizer. And here is a proposition which I will state now and sketch a proof tomorrow, is that the subgroup H of the mapping class group of S, maybe for this to be completely correct, I need to pass to a sort of finite index subgroup of the mapping class group, which is the kernel of the action on homology mod 3. But it's not super important. So up to working in the correct finite index subgroup of the mapping class group, I claim that the subgroup of the mapping class group is a curve stabilizer if and only if. Well, so what properties does the curve stabilizer have in the mapping class group? So first of all, it's a big subgroup, right? You can do essentially whatever you want on the complement of the curve. So H is non-amenable. But it contains the Dehn twist about the curve as an infinite cyclic normal subgroup. And H contains an infinite normal amenable subgroup. If you only say this could be any subgroup of the curve stabilizer. So to get the full curve stabilizer, I have to say H is maximal among all subgroups of the mapping class group satisfying this property. This is just to get the full curve stabilizer, not just a subgroup of the curve. And I claim that this is a characterization, meaning that conversely, you can prove that any subgroup that satisfies those two properties is a curve stabilizer. And here you see why on Tuesday I was talking about those amenable subrelations and normalized subrelations, because now I can just say that, well, here I formulated this proposition in a group theoretic way, but in fact, when you work with sub-equivalence relation, you have a way of just translating everything to setting of sub-equivalence relations, because you can say that a subrelation is of this form, if and only if it's non-amenable, it normalizes an infinite amenable subrelation, and it's maximal among all subrelations with respect to this property. And tomorrow, I promise that I will stick to the group theoretic setting. But right, the reason why I was introducing those definitions on Tuesday is just to tell you that there is a way of translating to the setting of equivalence relations that completes Kida's argument. Thank you.
Thank you. Any questions from the audience? Comments?
Okay, I'm writing xi. Okay, so this means when I write this restriction, it means so I view the equivalence relation. You can think it as a subset of x cross x, right? So I only take points where both extremities. Like I like to view when x and y are equivalent. I drew an arrow between them. So I only take those arrows where both the source and the target are in xi.
So what I'm saying is, this restriction is happening for all the rings that you are taking.
Yes. So for no, there is no xi cross xj. No, right. It's just, I cut and then I only look at each piece separately. So I'm not looking at, I'm forgetting all those. Yeah. I'm forgetting all, if X and Y here, they're equivalent, but I'm completely forgetting about this. Just cut into pieces and restrict to each piece. And nothing from, so right. So it's XI cross XI and XI. Yes. Just for simplicity, but I should have done with any coupling, just for simplicity of, but it doesn't change much. If you have an any coupling, it means that each of the two actions has a fundamental domain. You can always arrange so that you can kind of choose those fundamental domains so as to maximize the measure of the intersection. And then on the intersection of the two fundamental domains, the two actions have the same orbits. And then the X that you use would be this intersection. And everything works exactly the same way. Yes, that's true. Yeah. But it works the same way. In fact, so right. So I'm even cheating a little bit when I say I'm working with gamma, because I need to work with this finite index subgroup for things to really work. But it's true that, so the same characterization works for subgroup of any finite index subgroup. If you look at subgroups of this. But it's true that, I mean, right. For simplicity, I'm presenting the proof for self-couplings of gamma itself, but the same thing works for finite index. Yes.
Also distinguishes
Yes.
essentially the maximum flags.
Yes.
This one is also measurably distinguishing the maximum flags,
Yes.
so to speak.
Yes. And the proofs of the five, like out FN, hyperbolic groups, you always distinguish certain things that often have something to do with product regions. And this is where actually Adam's argument is really important, because product regions are the places where you have no hyperbolicity, and you can play this thing with, well, I'll explain the proof of this, but you can play this game where you let H act on the curve graph, and you start with your amenable subgroup to get some probability, you use barycenter. I mean, the Adam setting is exactly what enables you to distinguish the generic subgroups from those that come from product regions. In OutFN also, we work with product regions. In Arden groups, essentially, I mean, it's pretty amazing that the analogies between mapping class groups and Arden groups are very strong. It's exactly the same characterization that works for the subgroups we need. For Hickman groups, I say a word tomorrow. It's a bit more subtle, because in the Hickman group, every amenable subgroup has an amenable normalizer. So you cannot work with big normalizers. We have to do something a bit different, but still it's about locating the sub-relations coming from the Baum-Slack-Solitar subgroups. Yes. It's infinite. It's infinite. Yeah, you have, you can start with a curve and start applying powers of a pseudo Nosov, and you get infinitely many curves. It's also not locally finite because in the complement of a curve, you still have infinitely many curves. So it also has infinite diameter. In fact, so this is the theorem of Mazur-Minsky. It's hyperbolic. It has infinite diameter. Yeah. I don't know about. Yeah. No, so we can do things of the form like we have statements of the form if you have a group that acts on a cat-1 complex and you know you have sufficiently many information about the vertex stabilizers, edge stabilizers, how they intersect, and this kind of things. You can produce conditions like this to get MU rigidity, but I don't know precisely about setting them suggested.
That you try to construct maps from fundamental to transaction to something at the extent rather than you have other theorems. But specifically when you produce a countable partition, is there some motivation idea anything you have in mind when you're doing this?
Why do I need countable partitions?
No, I mean, why do you do it? Do you have motivation?
Okay, so I don't know if your question is about like, ideally you could say I'm trying to prove that the stabilizer of a curve for the first action is also the stabilizer of a curve for the second action. If you say it this way, it's not true. And it's true only up to a countable partition. The reason why you get countable partitions is because when you run this Adams type argument, you start with X to, you have a map from X to probabilities measures on something like the boundary of the curve graph, and then you start analyzing those measures. So at some point, you could get a map from X to, I don't know, finite sets of curves, right? We had things like that on Tuesday, map from X to finite sets of vertices in the hyperbolic. If you have this, it's usually convenient to say, well, it's a map to a countable set, so I can do a countable partition, and on each piece it's just one element. And so instead of saying there is an equivariant map from X to the set of, maybe I could say it this way, that there exists an equivariant map from X to the curve graph, such that which is invariant under S1C for the cocycle rho 2. But it's okay. It's maybe simpler to say that up to a countable partition where this map is constant on each piece, the curve is really invariant. Yes.
Okay, so let's thank Camille again.